Our displacement equation, which you've seen, we can write, it's a function of position and time. We can write it this way. Its amplitude is its bounds, and it oscillates sinusoidally at 2 pi x over lambda minus omega t. Okay, omega is 2 pi f, or we can write it as our angular frequency. All right, now we derived this by considering a pure sine wave at t equals 0. So it's coming out of the origin at t equals 0. That looks like this. Okay. And we started, this was t equals 0, and we started it there. But the question is, well, what if it starts not there? What if at t equals 0 it actually is shifted somewhat, maybe like that? Okay, and this is t equals 0. How do we take care of that? Well, it's quite simple. What it means is that this takes into account the wave moving. We derived it by having it move away from the origin. But if it's already moved away somewhat, we just need to add an extra bit. It's moving at these angular measurements. We just need to add a little bit. And so what we can do is we can say d of x and t is equal to the same amplitude, same sinusoidal motion. We have a 2 pi x over lambda minus omega t. That takes care of all of our spatial information, and that takes care of how it's moving. And then we just add what we call a phase constant. That's a Greek letter phi. It's a circle with a line going down. And we call it phi naught as our phase constant. Okay. And so we can think about if at t equals 0 and x equals 0, okay, so this is the case, t equals 0 and at x equals 0, if it's not 0, because all that's 0, if I'm not at 0, which is what sine of 0 would give, then I must have a phase constant. There must be something I'm starting with. And we'll try and figure out how do you determine that phase constant by looking at a graph and knowing the velocity. Okay, but this says how do you start? Now, because it's called a phase constant, it begs the question, what's a phase? Now, this entire thing is just called the phase, and that's just a fancy term to represent how far around the angle. It's kind of like, what's the total angular measurement I'm plugging into sine? This gives me some, this changes it, and this changes it some. And so it just tells me where am I starting on my circle. If this was the case, my phase constant would be 0, and then if I'm looking right here, the phase would be determined by this part. And then at a later time, if I'm looking right here, the phase is determined by not only the position, but also the time. Oh, I apologize, this was at t equals 0, but if this was the wave moving later on, it'd be determined by the time as well. And so the phase is just everything inside. It's the total input you give to the sine to say where are you at in position and time. So the phase constant is non-zero if at t equals 0 the wave is not coming out of the origin. It's not 0. Well, let me be a little careful there. There's one case that may sound like I'm lying, and I do need a little more accurate. What if I'm like this? That's coming out of 0, but it's coming out upside down. Okay, and that's actually a phase of pi, or of pi. That's halfway through the cycle. This wave has moved halfway, and so it's coming now down. So when I see coming out, or pure sine wave, it's got to be coming out through the top. So this would have a phase of pi, or a phase constant, I should say, of pi, when t equals 0 and x equals 0. It would be coming down out of the origin. And we'll do some more examples of how to find phi, this phase constant.